vaccinated. So, all right, so I just need to make sure that the, I should have brought this up first and making sure that everything is correct. But anyway, so today we're going to look at optimal binary search trees. Generally in the summer when I do this, I really only cover these three problems: the binomial coefficients, the 0-1 knapsack problem, and then the optimal binary search tree problem. These are the most, I wouldn't even say that they're the most practical problems, but the optimal binary search trees certainly are one of the more practical data structures that come out of dynamic programming. A lot of the other ones are kind of like toy problems, and once you've seen one dynamic programming solution, you've seen them all. So we can go ahead and I can go ahead and prep a couple more if you want to see more. Otherwise, this might be the last one we take a look at, leaving us with plenty of time over the next week to do to either start on the last topic or do some other things. Let me know what you'd like to do. But anyway, optimal binary search trees. This is not a balanced binary search tree. It's an optimal binary search tree. Like a binary search tree, you're given a set of keys. You still have to maintain their order, A, B, C, D, E, F, G, right? That's still the order, and you still have to maintain this binary search tree property. That if you have a key, everything in the left subtree is less, everything in the right subtree is greater than that key. You don't necessarily, however, want to balance the tree. In fact, it could be that the optimal tree is a completely unbalanced tree, right? Instead, what you're optimizing here is the minimum number of expected key comparisons. Now, to understand what that means, let's take a very, very small, simple example here, okay? And so I'm going to go ahead and switch over to the pad. All right, so let's suppose that we have a very small tree here. We have A, B, and C as our keys. Right? And say that we have a probability distribution on these. The interpretation here, 0.6, 0.3, and 0.1. The interpretation here is that 60% of the time you search for A. Only 10% of the time you search for C. And the other 30% of the time you search for B. All right? The application here for this particular data structure is that your keys are pretty much static. You're not going to be inserting a lot of stuff. You're not going to be removing a lot of stuff. And also up front, you have this at least estimate on this probability distribution. If you think about, say, I don't know, a typical Google search, somebody who's searching for sports. Searching for football is going to be a hell of a lot more, common than searching for shinty. Does anybody know what shinty is? No, it's kind of a. I think it's played in Scotland or Ireland or something. It's basically kind of like really old field hockey, where you've got these mallets and you hit the ball back and forth, right? I only saw it because I saw it on ESPN, the Ocho, right? That's not a real channel, but that kind of idea, right? So there are going to be things that are more common, and there are going to be things that are rarer. You want the more common stuff up here shallow in the tree because it will take you a fewer number of key comparisons to find it. The less common stuff is going to be down here deeper in the tree, right? With only 3 keys, how many possible trees are there? Well, let's take a balanced tree approach, A, B, and C. Remember that it has to be A is less than B, B is less than C, so you have to preserve the binary search tree property. What is the number of expected key comparisons for this tree configuration right here? Right? So when you're searching for B, you make 1 comparison to find the thing that you're looking for. So that has a probability of 3. And 1, so number of comparisons, and the probability. What about A? To search for A means that you have 1 key comparison for B to see that A is in the left subtree, 2 key comparisons for A to find A. And that's going to be 0.6. And finally, 0.1 also is going to be 2 key comparisons. Add those up, and what do you get? 1.7 key comparisons on average, right? Again, this is the key comparisons on average, or the expected number of comparisons. All right? So can we do better? Let me go ahead and repeat it over here. So again, it's A, B, and C with probability distribution 0.6, 0.3, and 0.1. How many trees can you how many binary trees can you form with 3 keys? What's another configuration that you could come up with? What if I put A as the root? Could I put B and C over here on the left subtree? Remember that A is less than B, less than C. Right? Nope. I would have to put over here in this tree B and C in some configuration. So what's one possible configuration? What if I put C next? Where do I have to put B? To the left of C. Right? Okay, there's another configuration. And what is the average number of key comparisons here? So the probability of A is going to be 0.6, and the number of comparisons is going to be 1. The probability of B is 0.3, and how many key comparisons here now? 1, 2, and then 3. So 3. And then 0.1, that's going to be 2 key comparisons, right? 1, and then 2, and then you found it and you're done. Okay? Add those all up. And what's that going to be? Also, I think 1.7, right? 6, 5, 6, yeah, 7. Okay. So no better than the balanced binary search tree. Nope, 0.9, 0.6, that's 1.5, and then 1.2, 0.2 added on to that. Right? Let's go with a completely different tree that is antithetical to what we've been looking for at with balanced binary search trees. Right? What if I did something like this? A, B, C. Right? Now how many key comparisons are there? Again, it's 0.6, 0.3, and 0.1, but only 1 key comparison for A, 2 for B, and 3 for C. Add all these up and what do you get? I think 1.5. Right? That's better, right? Because that's on average. But this is the worst possible tree with respect to balance. In fact, it's nothing more than a linked list, right? So, by the way, before we move on, what are the other 2 configurations that you could have? Completely skewed the other way, right? And C, and then A, and then B. Skewed, but in the other way. In fact, so this is 1, 2, 3, 4, 5. Does that look familiar? 5 possibilities with a tree with 3 keys. That corresponds to a balanced tree, a tree that is skewed to the right and then to the left, meaning that if you wanted to rebalance it in an AVL tree, it would be a right rotation, left rotation. This one is completely skewed to the right, so left rotation, right rotation, left, right rotation. Right? These are the 5 possible configurations with AVL trees with 3 keys. Right? And you'll find that indeed this one right here is the best that you can do with this particular probability distribution. Okay? But in general, if you're just given the probability distribution, how do you come up with the optimal tree? There are these things called the Catalan numbers. Right? Has anybody played around with combinatorics or taken a combinatorics class? Nope. All right. So the Catalan numbers, C sub n, is equal to 1 over n plus 1, 2n choose n. So now tell me about 2n choose n. Is that small? No, that's big, right? In fact, this can be shown to be order, what is it, 4 to the n divided by 1.5 to the n, right? Is that right? Or, sorry, no, n, otherwise that would simplify. So there's some polynomial value in the denominator here, but the dominant factor here is 4 to the n. This is going to be exponential. Why do I bring up the Catalan numbers? First of all, they have a lot of interpretations, like all combinatorial objects. They have multiple different interpretations. The Catalan numbers are going to be the number of possible binary search trees with n keys, right? And you can plug that in for n being 3, right? N being 3 is going to be 1 divided by 4 times 6, choose 3. Does anybody know what that is? Well, what should it be? As long as I'm not lying. Oh, okay, so let's go ahead and go with the full thing here. 6 factorial, 3 factorial, 3 factorial. And remember, there's still 1/4 out here. All right, so that'll be 6 times 5 times 4. So 6 times 5 times 4. That 4 gets canceled with that. And then we've got 6 down here. That gets canceled, and we end up with 5. I wasn't lying. 1, 2, 3, 4, 5. Right? But this is a very large number, right? If you were to enumerate every single possible tree configuration, come up with the expected number of key comparisons, that would end up being, of course, exponential here. Okay. And by the way, where does this come from? It comes from, I think, something called the Stirling approximation. Or if you've got what is it? If you've got something like 2 to the n, choose k, you can come up with a Stirling's approximation formula that does it in terms of factorial. N factorial would have a Stirling's approximation, something like that. Forget about it. It doesn't really matter. It's big, right? So you cannot go about this with a brute force enumeration kind of approach, right? So what we need is we need to come up with a dynamic programming solution for this. So here's the scenario. We're given these keys, K1 through Kn, and each one of them has a probability, P1 through Pn. Furthermore, we're going to say that the keys are already ordered. In your programming assignment, I think that we give you these keys and their probability distributions, but we don't tell you that they're ordered. So you're going to have to sort them up front first. Right? That's easy. Python, what is it? Sort or sorted or something like that? Yeah.
So should we sort the keys according to their probabilities?
No, you sort them according to how you would search. And I think that the keys in the programming assignment are going to be strings. And so you just use lexicographic order. Okay? So what we're going to do is we're going to come up with a recurrence here, C sub ij. That's going to be the optimal binary search tree for keys ki through kj. Let's visualize that over here. All right? So C sub ij will be the expected number of comparisons, comps for short, for an optimal binary search tree involving keys ki through kj. Right. So now let's think of, before we think of the full relation here, let's think of some corner cases. Right? For example, what is the full solution? What I and j do we consider? I want to involve all the keys, right? So the keys are indexed 1 up to n. Right? So C sub 1 n is the last solution that we're interested in. This is going to be the optimal binary search tree for keys k1 through kn. That's the one that we want. All right? What are some other corner cases here? Right? For example, I and j will run from ... 0 up to n. Why 0? We need a corner case here. So here are the base cases or edge cases or corner cases, whatever you want to call them. For example, what if I asked you about C sub 1, 1? That's the expected number of key comparisons for keys, optimal binary search tree, for keys K1 through K1. In other words, just that first key. What does that tree look like? Does it have any children? Nope. Does it have a parent? Nope. We call this a what? A single node tree, a seed, right? Whatever you want to call it. What does it cost you to search this tree? One key comparison. And what is the probability of searching for this key? Not if that were the only key, yes. But remember that you're given these probabilities, P1 through Pn. So the cost is one comparison times the probability of searching for that key. All right. You can do the same thing for C22, C33, ... So in general, C sub I is going to be the optimal binary search tree of key I, of only key I. And so that's going to be equal to 1 times P sub I. Okay? Here's another example. If I said C sub 1, 3, right, then that means it's going to have a tree involving K1, K2, and K3. Which takes us back to the original example that I started out with. If this is A, B, and C, how many possible configurations are there of that tree? 5. All right. All right. So what are some other edge cases here? What if I said C sub 0, 0? Is there such a key? Is there a key K0 through K0 according to what I gave over here? No. So what kind of tree is that? It's an empty tree. Sorry, come on. Right, this is an empty tree. And so what's its cost? What's the cost of searching an empty tree? How many key comparisons would you do to search nothing? 0. Right? Likewise, what if I have C sub, say, 0, 1? Right? In other words, keys K0 through K... sorry. What I want is 1, 0. This is keys K1 through K0. Do we work backwards like this? No, this doesn't make any sense. So this would be another empty tree. Yeah.
Is it an empty tree because it goes to 0, which doesn't...
It's backwards.
Or is it because
It's backwards. It's invalid. Remember that how we defined C sub ij. It's the expected number of key comparisons involving keys I through j, inclusive and in order. So 1 through 0, there is nothing, right? It's like asking, well, here's an array. What are the elements -5 through -10, right? Now, some languages support it like that. Python would allow you to do something like that, right? You can use negative, and it just wraps around. Or am I thinking of PHP? It works? Okay, yeah. Anyway, this is an empty tree, and so what's the cost? Also 0. Okay? So those are all the edge cases. When you've got a single node tree, when you've got an empty tree here. Yeah?
I thought you said K only runs from K1 to Kn, though.
Yeah.
So
1 to n.
from 0 to n,
Well, you have to have these for the edge cases, right?
Okay.
0 up to n, but the keys are 1 through n. So what is key 0? It doesn't exist. All right? You basically need to capture the cost of searching an empty tree. If I gave you this tree right here, like we started out with, all right, what's the cost of searching down here? 0, because you're at the end of the tree.
Okay.
All right? Okay. So now let's go ahead and get a hold on C sub ij. Again, this is involving keys keys I through key j. All right? Just given these keys, let's do one concrete example here: 2, K3, and K4. Right? In other words, if we were to consider 2 through 4, what are the possible tree configurations with this? We've already seen that if you only have 3 keys, how many possible trees are there? 5, right? How did we go about making those trees? We had to make a decision first. Do you make K2 your root, or do you make K3 your root, or do you make K4 your root? Right? And then if you on choice 1 here, if you make K2 your root, can you put anything to the left subtree? Not without violating those keys. Right? So everything would go over here in this structure, and that would be K3 and K4. Right? What if you made K3 your root choice? Then there would be some right subtree and some left subtree involving keys K2 and K4. And then, of course, because those are single nodes or single keys, that tree would end up being a single node. What about K4? There would be no right subtree, but this one would involve K2, comma, K3, somewhere in there. Right? So really, we don't have 5 choices. I mean, we have 5 overall configurations, but we don't have 5 choices. Right? If we're only looking at the immediate choice, all we need to determine is which one of these things is going to be our root. Because once we've chosen this root here, then we can look. Then we've reduced the problem. We've reduced the problem down to, well, what's the optimal binary search tree involving 2 through 3 and 4, or what's the optimal binary search tree involving 2 and 3? Right? We've cut it down in half. Right? Now let's look at this from from a concrete perspective. Let's look at this from a more abstract perspective. Suppose that my choice here is KL. So make KL the root, where L is equal to I, or I plus 1, or ... up to and including J. Right? You've actually got I plus 1, I plus 2, ... J choices here, however many that is. J minus I plus 1 or something. J minus I minus 1. So yeah, plus 1, like I said. What does that look like visually? By making this into the root, you have a left subtree. Cool. There we go. A left subtree involving Ki through KL minus 1, and a right subtree involving KL plus 1 up through KJ. Okay. And these now are 2 subproblems. This is a subproblem. And you ask the question, what is the optimal binary search tree involving I through L minus 1? Then you ask the question, what is the optimal binary search tree involving L plus 1 through J? Right? And you choose the minimum among all of these. But you have to be careful here, because suppose that we have the optimal value here for the subtree. Do we have a way to express that? C sub I, comma, L minus 1. That's exactly our definition of C sub ij. And this one is going to be C sub L plus 1, comma, J. But you have put a new node between these 2 trees. You have shoved this tree down here. Remember that this is the expected number of comparisons involving these keys right here. This is the expected number of comparisons involving these keys. If you're adding something above it, you are shoving this one down and making its depth one larger. What does that do to the number of key comparisons for this entire tree? It adds 1 to each key in there, right? So if my probabilities were p sub I plus 1, dot, 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 up to p sub L minus 1, right? Add all of these together because you're multiplying by 1 each and every single time. And that's your that's your additional this is the added cost. Oops. Sorry. Come on. Added cost for increasing the depth or the height, whatever you want to look at it. The added cost over here is going to be p sub L plus 1, p sub L plus 2, dot, 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 p sub k. Right? So this is the added cost. Right. So far we have this cost plus this cost plus this. Does that account for everything? We also have the cost of the root. That only takes 1 key comparison though. So p sub L. Right? By the way, you can simplify these. This and this and this. If you add all those together, what do you get? That's simply just the sum of, what was I using? I up to j of p sub, I need an index variable though, and I don't want to use k because I've already used k for the key. I don't want to use L because I've already used L for the break. M, p sub m, right? Now, does it matter where you broke? Did you like you could have broken it on the first one, or the second one, or the third one, dot dot dot, or the last one, right? Does it matter? Does this change? Adding all these 3 things together, that's the same every single time, right? What does change are these 2 values here. This one plus this one means, and then add on to the added cost of increasing the depth of everything, and that's the total cost. So all together here, c sub ij will be the minimum. And here, what variable? I think I use L here. Can I use L? Sorry, just I want to make sure. Yeah, L. So I less than or equal to L less than or equal to J of, give myself plenty of room here, C sub I L minus 1. Remember that that's this one right here. I and then L minus 1 plus C sub L plus 1 comma J plus, and then this term right here, which I'll just go ahead and go with, I guess in the notes I used S, so I'll go ahead and use S here. S is equal to I running up to J of P sub S. There we go. And again, why do we have to run L from I all the way up to J? Because each one of those things you could make the root. Okay? Now, what does this table look like? So, what I'm going to do is I'm going to run I and J. And because of that, run it all the way down here. Come on, there we go. And then all the way over here. There we go. I'm going to run I, running from 1, 2, 3, 4, dot, 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 up to n, and n plus 1. All right? We'll understand why here in a second that we're going 1 extra. I will run j from 0, and I'll explain why we do 0 here in a second, 2, 3, dot, 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 all the way up to and including n. Okay? So here's my table. Why did I include 0 over here? You need those corner cases. Remember this corner case over here where you have an empty tree, right? We need to take care of those. Where are the empty trees here? Well, the first one that I mentioned before was 1, 0, right? All along the diagonal, right? Again, what does it mean to include keys 2 through 1? That's backwards. So it's invalid, so it is an empty tree and therefore has a cost of 0. Right? So 3 and 2, 4 and 3, dot, 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 all the way down to and including n plus 1 and n. And that's why I went 1 extra. Otherwise, it would not be a square table here. Right? All of these are going to be 0 on the diagonal. Now, what about down here? What about the lower left diagonal? If you can't have a tree from 1 to 0, can you have a tree from 4 to 0? Nope. Can you have a tree from 4 to 2? Nope. So everything down here is completely irrelevant. Don't even bother setting it. Right? All you need are these base cases right here. Now, what about the other base case, where you've got a single node tree and you just need to fill in the probability here? That's along the next diagonal, right? So p sub 1. Why? Because this is the tree including 1 through 1, 2 through 2. So this is p2 and p3, dot, dot, dot. This one is going to be p sub n. Right. Which is the one that we're interested in, though? Where's the last final solution here? All the keys. Keys 1 through n. This is the one that we're interested in. C1n. Right. So the base cases take care of the diagonal and then the next diagonal right above it. Top left to bottom right. The last solution that we're interested in here is this. This is the optimal tree. This is the cost of the optimal tree. How do we go about filling these in? Well, let's think about what C sub ij looks like. I'll put it right here. C sub ij. So let's think of this as j, and I've written it in the in this area where it's 2, but let's just think about C sub ij here for a second. Okay. What does it depend on? It depends on I through L minus 1 and L plus 1 through j. Right? What does that look like with respect to this table here? It looks like the following. And let me go ahead and give myself another color here. There. All right. So you have I through j, and you can make the first one your root, meaning that everything else is in the right subtree. Right? The one that corresponds to is taking this as the root, and then looking down here, and these two match right here. Right? This is the cost of making the leftmost one into your root, and then shoving everything down into the right subtree. The second one, if you make that the root, then it's this value right here, and then compared to every value down here. Oops, sorry. All right. The third one will be compared to this one over here. I want to make absolutely sure I've got this. Yep, this is right. Dot, dot, dot. Until finally you have this one right here and the one right next to it. That corresponds to making the rightmost one your root and then shoving everything else down into the left subtree. I think I've got a much better representation of this. Come on. There you are. There it is. Right. So again, the left, you're making this into your root, or you're making I into your root. So what are you shoving down into the left subtree? Nothing. I through I minus 1, that's going to be the empty tree. That's going to end up being 0. Right? And then you need to put everything else into the right subtree. So that's I plus 1 through j. Right? If you end up making, let's see, this is going to be I plus 1, the second one into the root, then you need to look at the cost of putting k sub I over here and then all the rest of them over here, which is going to correspond to this one right here. Right? So here's the dependency. Right? Each one of these is dependent on something in the same row and then something in the same column right below it. What does that suggest about the way that we have to fill this out?
Start from the right top corner.
Right top corner?
No,
Or
sorry, the left.
left top corner. Right? And then what? I have to have all of these values, and I have to have all these values in order to get this value right here. The way that I filled in the base cases was top left to bottom right. Top left to bottom right. And that is exactly the order that you fill them out with all the rest of them. Right? Now, I don't know if you're jazzed about coming up with the loop to do this. I would encourage, it's a nice little exercise, but otherwise it is also presented in my notes, the book, right? And there it is. Right? We're just going to go through and annotate this and analyze it. I don't want to have to bring to redo it from scratch. Mostly because also a couple of years ago I did an extensive lecture on this. I think it was an hour or maybe 2 hours or so, and then I did it over in the Light Table studio a while ago, and I'll publish. I'll provide a link to it. But has anybody ever seen or it's not the light board? I guess it is. It's not a whiteboard. It's the light board. Has anybody seen that before? In a class? Where have you seen it?
Oh, I just watched the video.
Whose? Like, oh, my video? that's the only one I've ever done in the Light Table. But it's this table. It's this. You draw with these iridescent markers, and then it's backlit. So you're drawing in front of you, and then the camera's on you. But of course, then because you're writing like this, the camera's like this. Everything is backwards. So in post-production, you have to flip everything. And that means that this would end up being backwards, and so I had to go out and to a T-shirt place, and I asked them, "Can you print a UNLN but backwards so that when I flip it back, it'll look nice?" And they go, "Yeah, we could do that, I guess." And so they did it, and I bought a $20 sheet T-shirt with an N on it, a backwards N though. I ended up only using it once. Yeah, I think I've got maybe a quick sort video or something. I was testing it out. It never. I mean, it's still available, and but it was never grew in popularity. I don't know why. It's a pretty cool setup, but whatever. Anyway, that's in those videos if you want to check those out, and I'll make sure to post them if they're not already in Canvas. But in any case, we derive this this algorithm right here. Let's walk through it and analyze, or not analyze it, but let's annotate it. Right? So this is the initialization. What are we doing here? What about this first one? What about this first line right here? That's setting that diagonal, right? That is an empty tree. Equals no cost. What about these? These are the single node trees. Right? So the cost is equal to P sub I. Right? Or in this case, I've used the notation P sub, the probability of searching for key K sub I. What is this thing right here? I'll annotate that way over here. This is the root table. So do you remember with Floyd-Varshall's algorithm? You had to keep track of a successor in order to rebuild the path. Or with Dijkstra's algorithm, you had to keep track of a predecessor in order to rebuild the path. We're going to have to keep track of the choice that we took when we made this decision right here. which L value gave us the minimum value here, right? And we're going to have to keep track of that in order to rebuild the tree. Right? So that's going to be our root table. Right? It keeps track of the node that gave us the minimum. Okay? And if you only have key I, well, what's your only choice? I. Right? And so that's the initialization there. We also have this one last corner case here. All that's doing is setting this value. Oops. All that's doing is setting this value here because it's not enough with that loop. Otherwise, the loop would be more complicated. Okay. Then we run from D, running from 1 up to n minus 1, and then 1 up to n minus D. That's the magic right there. That's the magic that gets you top left to bottom right, top left to bottom right along the diagonals. Right? That gives us I and J. Right? And you just, I'm sure that there are other equivalent ways of doing this. I just sat down one afternoon and said, okay, how do I change these indices so that I get this top to bottom, top left to bottom right, top left to bottom right, right? So you don't have to do it, right? But go ahead, reproduce it. It's a nice little exercise. How do you iterate over a matrix column-wise? How do you iterate over a matrix row-wise? How do you iterate over a matrix diagonally, and then diagonally the other way, right? For various operations. Okay. But otherwise, we start out with a very large number in order to find the minimum. And then we run from L, running from I up to J. We're going to decide which one of these is best. That we consider each K sub L is our root. Right? And all we're doing here is taking these two other values. We're not worried about this value because that's invariant. That doesn't change depending on what your choice of L is over here. So what I've done in the pseudocode is I've held that off until the end. It's not going to affect the minimum at all. And all we're doing is taking those two other values, putting that in the queue. If Q is less than the minimum that you've found so far, then you update the minimum and you also update the root table. L is the value, the key value that gave you that minimum. Okay? Once you're done with this inner loop here, you've found the minimum, and the cost of C sub ij is going to be that minimum plus then there's where you sum up all the elements from I up to J. At the end, you output C sub 1 to n. That's the final one that you're looking for. That's the cost of the actual tree and the root table so that you can build the tree. Right? So how do we go about building that tree? And also, let's look at an example. Unfortunately, with only about 5 minutes left, we're not going to get to it. So any questions on what we've looked at so far? No? Go ahead.
So we're doing this so that we can divide the problem up into sub-problems.
Yep.
So that then for each problem slash sub-problem, we know the root.
Right.
And we know what the children of, or like.
Well, let's take an example. Key 1 through 5. Right? In fact, this is the example that we're going to look at next time. You have to decide what's your what's going to be your root first of all, right? Suppose that it's key 1. That means that you've got a subtree over here with keys 2 through K5. Right? I don't know what the optimal binary search tree for that is. That's why you recurse. But then again, it's dynamic programming. We're not going to recurse. We're going to invert the recursion so that we're building this table instead.
So the root table has the table of roots that are used for each
Yep.
thing, and then using the data from the root table, you can jump to another place on the
Yeah, actually, I won't even show you the recursive version of that. I'll still keep it so that we have an iterative version, and we'll use a stack instead.
Okay.
But this is the idea. You could make K1 your root, or you could make you could make K2 your root, or you could make K3 your root. In which case, over here you've got what keys? K1 through K2, and over here you've got K4 through K5. And you've got two more choices, K4 and K5, right? Which would look like this one but reversed, mirror imaged, and this one but reversed, mirror imaged. But you've broken the problem down into two subproblems. If I make this my root, then what's the optimal binary search tree involving these keys over here, and what's the optimal binary search tree involving these keys over here? If you were doing this recursively, you would recurse on that tree, you would recurse on that tree, right? But we don't want to do it recursively because that would probably take us back to the Catalan numbers, actually, right? Where you're trying every single possibility. You're not actually even trying every single possibility. You are recomputing the same trees over and over and over again. That's why we put them into a table and reuse those values, right, implicitly. Okay? All right. We will start there next time.
Got it.